Hi students, this is Shivakrishna. Today I am explaining the topic about second unit, that is stresses in flexible payment. Already we are discussed in first unit, that is factors affecting in the payment design and how to design the payment in various factors and what are the factors influencing the payment selection and payment design and EAL, ESAL and tire pressure, contact pressure and traffic analysis and ADT, AADT. This all terminology we are discussed in the first unit, and we already know about the types of payment in the payment design. Generally, three types are there: flexible payment, rigid payment, and composite payment. In coming to second unit, the stresses in flexible payment. Flexible payment consists of 4 to 5 layers. These layers should subgrade, subbase, base codes, varying codes, and surface codes. In this consist of 4 to 5 layers. The stresses acting on that payment should be very high level. In this situation, the stresses will be acting on that surface of the road. The bearing strength of that surface codes should be capability maintain very high. In these stresses in flexible payment, first of all, we know that vehicle payment interaction. In this vehicle payment interaction, it should be thoroughly acting on the surface of the payment. Surface of the payment, it is a greatest material, that is bitumen or tar or modified bitumen. It should be used in the surface course material. In this, here consider vehicle payment interaction. One vehicle should be acting on that payment. That interaction should be capable or not. That interaction, it will be acting on the surface of the road. It will be considered very major role. Major components of the vehicle road interaction mechanism are the vehicle suspension system with the pavement surface. Roughness generates the friction and it carry the dynamic loads acting on that pavement. In this scenario, the loads transferred from the vehicle to pavement through the tires. The contact stresses on the pavement surface and geometry of the loaded area are thus affected by the tire type and inflation pressure. This both type of the tire and pressure on that acting on the surface of the road very major role acting on that pavement interaction. For this scenario, the stress strain induced in the pavement by the contact stresses on the surface is controlled by using the geometry and mechanical properties of the pavement layers. Know the every individual layer properties. You have to maintain particular region. It is very important. In this payment interaction, two approaches dealing with the problem for moving loads on the payment are presented. Finite element analysis has utilized for both approaches. For this analysis, this is the vehicle, that vehicle passing on the existing pavement. The friction developed between the tire of that vehicle and surface of that road, it should be maintained carefully, and the friction developed between the tire and surface of the road, it should be capable to each other and maintaining the particular contact between the both tire and surface of the pavement. Due to this friction only, the riding is very smooth and it should be capable to safely reaching the destination. In this, stress induced factors are very important, play the major role. These stresses, vertical stresses in these flexible pavement layers are vary with base course thickness. Stress and displacement decreases with higher frequencies and load amplitudes. The load should be capable very high. The stresses are very high and strains also very high acting on that particular road pavement. For this, especially when geogrid reinforcement is applied, the Applied on that, the stresses in the flexible pavement are influenced by the loading frequency and affecting the deformation levels. The acting on that load on the pavement, the stresses and strains should be acting very clearly. So here this figure shows the wheel load acting on the surface of that road, how much area it will be contacted through that tire, that should be categorized as the contact area. This contact area, it should be that load should be transferred to layer. Here the triangular portion or cone shape which will be formed in the load distribution scenario. So this is the approximate line or wheel load distribution. Here the load should be transferred through grain to grain, that is wearing course, base course, sub base and subgrade. It will be layer will be increases, the stress distribution on that particular area, it should be wider area should be acting on that particular location. This compared to surface layer and subgrade layer, the surface layer contact area is very less and the subgrade contact area is very more to transfer the load distribution. Stresses in flexible pavement. The stresses in the response of the loading on the pavement, material of the subgrade and environmental conditions are very highly responsible for determining the stresses on the pavement. These are the various types of stresses yields in flexible and rigid pavements under the applied live loads or dynamic loads and moving loads. The topmost paved surface in the such type are flexible and it is extremely depending upon the underlying layers like subgrade, subbase, base course, wearing course and surface course. Due to this flexible, pavement is free to move. In such type of pavement, following stresses are the most common and extremely affected. So these mainly three types of stresses will be acting on that particular flexible pavement, that are vertical stresses, shear stresses and radial stresses. Vertical stresses. What is meant by vertical stresses? The vertical stresses the pavement by compressing the pavement material. When the pavement compresses, the material of the pavement gets crushed and the result rutting become visible on top of the horizontal pavement. And coming to shear stresses, it is occurs on the pavement when the load is more than the capacity of the pavement. When the capacity of the pavement is more, in this develop the shear stresses. When the load approaches in the critical point, then as a result movement occurs in the base layer and that movement responsible to the shear stresses in the top of the pavement. And coming to radial stresses, in this bottom layers due to seepage, removal of the material from the particular layer by any other main, as a result fatigue cracking it should be visible on that surface of the pavement due to wear and tear actions on that particular vehicle. This type of layers, the three types of stresses will be acting on that particular pavement, that is the vertical stresses, radial stresses and shear stresses. These vertical stresses, radial stresses and shear stresses will be acting simultaneously on that particular cross section of that pavement. This type of distribution will be acting on that particular coordination system. Next, what is meant by viscoelastic theory? Viscoelastic theory, it is a framework, it is a describe the material. Here two parameters are involved particularly, that is viscosity and elasticity. In this viscoelastic material, it should be elastic behavior and viscous material in that applied materials. This theory particularly useful in understanding how materials deform and recover over time under various loading conditions. Here a more detailed look in the key concept, that is the elastic behavior and the second one viscous behavior. Coming to elastic behavior, bitumen has some elasticity nature and aggregates also having some elasticity nature. Both this material depending upon the material size and shape after applied the stress is removed. Once the stress will be acting on that pavement after releasing the load, what type of shapes it should be changed? It here I have to see that this behavior is described by Hooke's law. What said that Hooke's law? Stress is directly proportional to the strain. When that stress should be acting on the pavement, the strain should be acting per particular stresses only. Here, next coming to viscous behavior, materials deform continuously under stress and don't return the original shape. Viscosity nature does not coming to the original shape. In this here, the stress is removed. This characterized by material viscosity, which is related to rate in the strain of over this time. Next, what is the assumptions in viscoelastic theory? Here we are considered some more assumptions like using that materials are maintaining homogeneity and it maintain the distribution in all directions, that is isotropic. Next, linear behavior. When the load applied on that particular pavement, the loading distribution should be maintained as a linear. Non-uniform should not involve in this particular mechanism. Next, small deformations. Small deformations means when you are applying the load on that particular such pavement on the layers, deformations should be followed, not any particular deformations. So here next, linear superposition principle and no permanent damage. Here we are considered not only any permanent damage, it will be why, because we are retrofitting and rehabilitation to that particular pavement. Next, the stress and strains should be acting homogeneously. Next, layer system concept. In this road pavement system, the so many layers are involved here, that is subgrade, subbase, 4 to 5 layers are involved here. This layer system concept, it should be the stresses and strains developed on that particular region. The stresses and strains, it should be characterized into layer system, means that is the single layer system and 2 layer system and 3 layer systems it will consider, and every layer should have to find out the deflection and stresses and strains on that particular layer, and it is very complexity to maintain the one particular layer. So we have to decide to divide the layers and find out the stresses acting on that particular pavement. So in this layer system concept, generally 9 types of stresses should be acting on that particular pavement, that are 3 normal stresses and 6 shearing stresses. At each point in the system, there exists a certain orientation of that element, such shearing stresses acting on that each phase should be 0. The normal stresses under this condition or principal stresses are denoted by sigma 1 major axis and sigma 2 intermediate and sigma 3 minor axis. First of all, coming to multi-layer theory, this total pavement should be considered into 3 layers or multi-layer. Every 2 layers should be, or every 1 layer should be considered as a single layer. That number of layers should be involved here. So this total we are considered as a multi-layer theory. In here, assumptions have to find out that the material properties each layer are homogeneous and the property of the point AI is the same as the BI. Where that location, stresses and strains should be acting on that pavement, all the points should be equally distributed. And the next one, each layer has a finite thickness except the lower layer. Why? Because the subgrade material has a infinite thickness, remaining all top of the layer should be finite thickness, you have to assume. Next one, each layer is isotropic and the specific point AI is same every direction and orientation. And the stress solutions are characterized by 2 properties of that each layer, that is Poisson's ratio and Young's modulus. Next, one layer system. this total pavement should be considered as the single layer only. So here the stresses and strains should be acting on that total layer should be considered as the one layer. This should be total this one layer system studied on the Bosnick's equations were applied. This totally developed by Bosnick's only. Next, Bosnick's equations are developed for computing stresses in a homogeneous, isotropic and elastic medium. Pressure is maximum at shallow depth and theoretically becomes zero. We are depth increasing, the infinite depth increasing, the pressure also decreasing. Here load is applied, not a point load. Total distributed load should be acting on that particular scenario. Variation of stresses follows the same general pattern, and it should be one layer theory can apply an approximation for a conventional flexible pavement with granular base and subbase with a thin asphaltic layer and stiff grade comparable to base and subgrade. This is the displacement chart for finding the deflection of rigid and flexible plates we are using on that particular ratio. We are finding the deflection on that particular scenario. The total in that particular deflection, how can you find out means by using the flexible pavement, we are using the some conventional formula, that is 1.5 P into F by E. E means Young's modulus, F is the displacement factor. How to find the displacement factor here? Here some of the curves will be drawn here in the chart, that is E2 by E1. Every layer should have a different Young's modulus, so that's why E2 by E1 we have to get it from that equation, and H by R. H is the thickness of that pavement layer and R is the radial stresses on that particular pavement and area of the pavement. Both using this both values, you have to find out the displacement in the y-axis. Next, these equations we are using the finding the deflection in that particular scenario. When we are using the flexible plate, we are using the equation of 1.5 Pa by E2 into F2. When we are using the rigid plate, 1.18 Pa into Pa F2 by E2. When you are using flexible pavement using this formula and a rigid plate using this formula. By using this graph, we have to find out the displacement factor, that is the F2 we have to find out, and this by using this equation I have to find out the vertical surface deflection in these two layer concepts. These concepts should be developed by Burmeister theory, but Burmeister also assuming some precautions, that is the every layer should have maintained isotropic and homogeneous, and he is also assumes that a subgrade is the infinite thickness and remaining all of the top layers are finite thickness. Okay, thank you students.